Hello. You should see the desktop and hear me now. Does that seem okay?
Yep.
Yeah, okay. Okay. All right. I'm pulling up Windows. All right. Okay. Um, so let's see. Where are we? The homework assignments due today. And I've got assignment 2 up there, but it's not actually up there yet. And assignment 2 needs language 3. And today we're going to talk about language 2 and maybe start language 3. So, we're not really ready for assignment 2 anyway. So today we're going to start talking about language 2 and start a little bit with language 3, and then your programming assignment will be language 3. Okay. And I've already downloaded language 2. I have language 2 here and language 3 here. So we can start talking about them. And actually, I should also include language 1. And actually, the first thing I should do is I realized that it might be a good idea to summarize these languages. I just realized that you don't know what's coming up. So I wrote I'm going to put a link to it on the website. I wrote a brief description of what we're doing. So let me get it. Um, Okay. Here's a little table of contents of what we're doing. Okay. We're going to define a sequence of languages. Okay. Language 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And what we're doing is we're growing. So every one of these languages has all the languages before it as a sub language of them. Okay. So we started with a language of trees. Okay. So the language of trees lets us describe the tree data structure. Okay. All of these other languages are going to be examples of a tree language. And essentially, tree languages are what we mean. If you want, you can think of these as simplified versions of Lisp and Clojure and Scheme and Racket. These are famous examples of tree-like languages. All of these are a little bit more complicated than our tree language, but that's where the idea comes from. Okay, so then we start specializing the tree language, and we describe a language of integer expressions. Okay, things like the addition of 1 and 2, or the product of 3 with the sum of 2 and 3. Yeah, yeah. So that's a arithmetic expression, and that's an arithmetic expression. So it's a language of arithmetic expressions written as trees. So another way to think of this is the language of prefix arithmetic. Okay, so you could think of it as the language of prefix arithmetic. You put the plus operator in front of the operands. You put the multiplication operator in front of its operands, and see the plus is in front of its operands. Prefix notation. Okay, so the tree language is also a language of prefix notation. So it's a form of prefix notation. Okay, now language 2 adds another data type and more operators. So it's arithmetic and Boolean expressions. What that does is it takes this language and from the point of view of programming languages, what we're doing is we're giving the language a new data type, and we're giving it new operators that use that data type. So this language will let you do things like the anding of true and false. True and false are new literals. Like, the language arithmetic expression has integer literals. The language of Boolean expression has true and false literals. Or you could do things like or equal 3, 3, and the sum of 1 and 2. Yeah, with the less than symbol of 6 and 3. Okay, so there's a Boolean expression. The ORing of two things. The ORing of the equality of 3 with the sum of 1 and 2. So that's one of the things you're ORing. The other one is the inequality of 6 and 3. Is 6 less than 3? Okay, yeah, so that's a Boolean expression written in prefix form. So there's a Boolean expression. So that's language 2. So language 1 is just integer arithmetic. Notice that Boolean expressions need arithmetic because of things like the equality operator. The equality operator returns a Boolean, but it takes in integer operands. See? The inequality operator returns a Boolean, but it takes in integer operands. So we start with we could define a Boolean language before an integer language, but a Boolean language by itself is really boring because it only has the values true and false. And then you can just do and, or, and not of true and false. To get an interesting Boolean language, you need arithmetic ahead of time so you can do the Boolean of arithmetic expressions, like doing equality and inequality. Okay, so that's starting to get to be an interesting language. It's got two data types, integer and Boolean, and you can build up some pretty complicated expressions in it. Okay. Then the next language, this will be the language that your homework assignment is going to be based on. It has global variables. Okay, so you'll be able to declare, essentially, the language will let you do things like say, var x5, var y3, sum of x and y. So it'll be a language but now it'll be a language that also adds sequences. So you'll be able to say in a sequence, let x be 5, let y be 3, now take the sum of x and y. So we're going to add global variables to the language and also add sequences of expressions so that you can do this first, then do this, then take their sum. Okay, so that'll be language 3. And then your homework assignment is going to be, you're going to create a language 3A. Your homework assignment is to create a language 3A, which is language 3 will be language 3 with a couple new operators. I think if I remember right, you're going to add a plus plus and a minus minus, the operators. And I can't remember. I don't remember right now. I haven't looked at it in a couple weeks. But you're going to add a couple operators to language 3. Okay, so your homework will be language 3A, which is language 3 with several new operators. Okay, several new operators added to it. Okay, then language 4 is going to let us create local and global variables. And we'll see what that starts looking like. We'll have local. Remember, in almost all programming languages, you have variables that are local. Now, this language doesn't have functions yet, so those are not function variables. We'll see what we mean by local and global variables. Okay, and then language 5 is going to give us what's called lexically scoped variables. That's another. It's a better form of local and global variables. We'll see. So we're going to go take local and global variables and make them lexically scoped variables. Then we're going to add if statements and loops to the language. Okay. So have a language that has local and global variables that are lexically scoped and integer and Boolean data types, and it's going to have conditional expressions and loop expressions. Okay. And then language 7, which is a big jump, we're going to give it functions. Okay, we're going to give that language functions. At that point, we'll have a baby version of C. We'll have a baby version of the C language. It'll be C without struts or arrays. Okay, but it'll be a fairly sophisticated language. Okay, and then we're going to give that language what's called first-class nested and anonymous functions. Okay, at that point, we have a baby functional language, like JavaScript, okay, or Scheme. So language 7 is going to be a baby version of C, and then we add another feature to it. It's actually a pretty straightforward thing to do. We're going to add one more feature to it, and then it becomes a baby functional language that you can actually write some pretty sophisticated code in. Our language 8 is going to actually be a real programming language. It's almost like a baby JavaScript. Yeah, if this one's going to be baby C, you could think of this one as baby JavaScript. JavaScript without objects. Okay, so just like this will be C without struts and arrays, this will be JavaScript without objects, but it's a baby functional programming language. Okay, and then this one adds a new data type, the list data type. Okay, so at this point we have baby Lisp, because or if you want, it's still also JavaScript or Python. It becomes kind of a baby version of Python, baby Lisp, Python, and it's actually pretty sophisticated. Language 9 can run simple Python programs. We can take simple Python. We'll be able to, when we get there, we'll take simple Python programs and we can translate them into this language 9. Okay. Just like we'll be able to take simple C programs and translate them into language 7. Okay. So that's what we're going to do. We're going to build up, and every one of these like every language 6 program is a language 7 program. Every language 7 program will be a language 8 program. So the languages are growing, and all of them are tree languages. So we're going to be using the same syntax. Then if we get this far, I think we should. The next thing to do would be a language. Usually what I do is go back to language 7 and give it a C-like syntax. Language 7 that's no longer a tree language, so we'll call it language 7 infix, and then we'll be writing in traditional infix notation. Yeah, at that point you'll write var x equals y plus 1. You know, you're using regular, instead of writing var x plus y1, yeah, instead of writing a tree language, we'll go to infix language. So we'll go back to language 7 and give it what we call the surface syntax of traditional programming languages. But the thing, and then what we have to do is we have to write a parser. We'll have to write a much more complicated parser, because we're going to have to parse a more complicated language than tree languages. Okay. All right. So that's usually what we get to, that's about how far we get usually in this class. And if we have time after that, we can actually go back and write a compiler for one of these languages. You know, it's okay. Writing a compiler for this language is way beyond the scope of this class. And writing a compiler for this language is way beyond the scope of this class. Writing a compiler for this language is kind of hard. Okay. We can maybe write a compiler for is go back and do one of these languages here, 4, 5, or 6. Okay. Because compilers are harder. What we're going to be writing it all along here are interpreters. So we're going to write an interpreter for every one of these languages. A compiler for every one of them is harder. Okay. A compiler is harder. So the last thing would be a compiler for, say, language 4. Yeah, a compiler for that language, or even go back. Even an interesting case is to go back all the way to language 3 and write a compiler for the language of integer and Boolean expressions. Okay. Instead of writing an interpreter, write a compiler for that language. So then you would compile and you'd get an exe program. Yeah, and then you could run the exe program. that would just calculate an integer. It would be an exe program that does nothing but calculate an integer expression, but it would still be taking an expression, compiling it, and then running it. Okay, so now we've done mostly this, this is what we've done so far. We've done kind of like languages 0, 1, and 2. Well, we've been working with language. No, actually, we haven't done language. We've only done languages 0 and 1 so far. So let's start talking. Well, let's talk about language 1 and talk about language 2 a little bit today. Okay. All right. So this is the stuff that describes language 1. Okay. Now it's a lot of files. Okay. And this is your textbook, really, to read this code and understand this code. And that's where programming assignment 2 is going to come in. It's going to more or less force you to dig deeper into this code for language 3. Okay, but let's try to go through it real carefully again. Okay, so let's do it by starting at the top level. Here is a program that is going to evaluate that arithmetic expression. So that arithmetic expression is, well, that's what its tree, that's its expression tree, and the arithmetic expression is written this way. Okay, so it's the sum of a product of 4 and 5, with the integer, with the remainder of 100 divided by 15 minus 5. Okay, all right, so there's the integer arithmetic expression, and there it's written in its prefix form. Okay, so that's a statement in our language. Okay, that's in our language. So we build the tree. So now this is just language 0. So far, this part here is no different than language 0. Take that expression and build that tree out of it. Okay, so that's what parse tree does. Okay, so parse tree in language 1 is exactly the same as parse tree in language 0. It takes a tree expression and builds the tree out of it. Now, this tree expression happens to be also an expression it's an arithmetic expression, but it's an arithmetic expression in the tree language. Okay, so we've got a tree that represents that arithmetic expression. Okay, now we want to evaluate that tree. Okay, now here I print out the tree. Okay, that's no different than language 0. Here we pretty print the tree. Okay, that's just like language 0. Okay, let's skip over this one for a minute. This just does the pre-order and post-order traversals of the tree. That's just like the tree language. The one that's really interesting for us is this one. We want to evaluate the tree. That's the interpreter. Okay, so interpret, or another way to say it is evaluate. Most programming languages refer to this eval. They abbreviate evaluate to eval. So this is the eval function. There's an eval function built into Python. There's an eval function built into JavaScript. They have built into them an eval function. Okay, all right. So we want to evaluate our tree. No, so we don't evaluate this thing. The whole goal is to make our life easier by saying, take that thing, build a tree for it, then evaluate the tree. Okay, because evaluating the tree more or less is one of these traversals. To evaluate this tree, you do it recursively. How do you add two things? Well, first you need to know what the left thing is. So evaluate of plus says evaluate the left thing recursively. And evaluate a plus says evaluate the right thing recursively. Now I've got a left thing and a right thing, and I add them together and I'm done. All the work, so evaluate's real simple. To evaluate an operator, you evaluate its left operand, you evaluate its right operand, and then you do the operator on the results. Okay. So then when this guy tells this guy to evaluate himself, this guy gets his left operand, but that's easy. The left operand is a literal. So his left operand is a literal, so it's 4. Then he needs to get his right operand. His right operand is a literal, that's 5. So now he can do 4 plus 5 is 9 and reports 9 back to this one. Then Notice that what we're doing is a post-order traversal because he's not done until after he first does the left, then does the right, then he can do, so he's doing his work after doing the left and the right work. So that's a form of a post-order traversal. When he has to do his work, he tells his left branch to evaluate itself, but the left branch is a literal, so it immediately returns its value. Then he asks his right branch to evaluate itself. Well, the right branch recursively says to its left branch, evaluate yourself, then says to its right branch, evaluate yourself, and it gets its answer. Okay. Now, so that's all done. Let's look at the code for that. That's in the evaluate method. Okay. Now, I think I mentioned in class the other day that this evaluate method is harder than it should be because it's actually doing a lot of error checking. The evaluate method is assuming that it could be given a mangled tree, okay? And the reason is that because this tree expression could have been mangled. You know, there could have been something wrong with it. For example, the plus operator maybe didn't have two operands, you know, or yeah, there could be something wrong with the expression tree. Now, if we built a more sophisticated language system, we could have this parse tree function not parse a mangled tree. But in our system, parse tree parses anything that's in the tree language. So for example, if you give plus one operand, that's still something in the tree language. That's still in the tree language. That's a root with one branch. Okay, so that's a tree. So parse tree will build that tree. So that would look like this. Okay. Now, but that's mangled. You can't multiply 4 with nothing. Okay. So whose job is it to figure out that that's a mangled expression? In a more realistic sense, it should be this parse tree that would figure that out. But to keep parse tree simple, we're putting that responsibility on evaluate. So that makes evaluate more complicated. And it's kind of 6 of one, half dozen of the other. You could either make the parser more complicated or you can make the evaluator more complicated. Either the parser figures out that the tree is mangled or the evaluator figures out that the tree is mangled. We're going to put the work in the evaluator. And in fact, a lot of programming languages do it that way. A lot of programming languages, instead of having the parser do a lot of the grunt work of figuring out where mistakes are, they leave it up to the evaluator. Okay, that's that's what languages like Python and JavaScript do. The languages that are not compiled languages. They tend to put more error checking responsibility in the interpreter and less in the actual parser. Okay. All right. So we will have we're going to stick to a dumb parser that parses anything that's a tree. But then we're going to make our evaluators evaluate the trees carefully, making sure that they're structured properly. Okay. So I could make the evaluate, and I think I've been meaning, I said this a couple of times, I think I will do it. I'll write a version of the evaluator that doesn't do any error checking, that works when it's given a perfect tree, but blows up and crashes when it's given an imperfect tree. But then you can see the logic of the evaluate part. Right now, you've got the evaluate logic mixed in with a lot of error checking logic. Okay, so let's look real carefully at the evaluate logic mixed with the error checking. Okay, here's a summary of the language we're about. Yeah, this thing's evaluating the language of addition, subtraction, multiplication, division, integer division, and exponentiation. That's well, this is integer division. This is the quotient operator, and this is the remainder operator. Okay, quotient, and remainder. Okay, addition is going to take one or more parameters. Subtraction is going to take one or two parameters. So, because it could be unary negation. This is either subtraction or unary negation. Multiplication could take two or more parameters. It makes sense to multiply 3 numbers. It makes sense to multiply 5 numbers, but it doesn't make sense to multiply 1 number. Okay, so this thing takes 2 or more parameters. division doesn't, it's hard to make sense of division of more than two numbers. I mean, there is, some languages do let you write they do let you say something like, okay, from our point of view, that makes sense. It's just 3 times 4 times 5, okay? That's a little bit trickier to figure out, okay? Does anybody see why this one's trickier than this one? We won't do this one for a reason. See if anybody can, what, and the same thing with, okay, here's a better hint. This is easy to figure out what that means. This is not so obvious. What is it about this guy versus this guy and this guy versus this guy that makes us not want to do, this is okay, but this one's kind of not okay? But it's not entirely not okay. So I should say kind of not okay. What is it that makes this one harder?
Well, multiplication and addition will always be the same no matter what order you do the summing or multiplying of the numbers.
Yeah, and?
But in division, the order matters.
Right. Yeah, and since the order matters, this could get very confusing. Because what you think minus 4, 5, 6 means and what I think minus 4, 5, 6 means can be different. So it could be either 4 minus 5 minus 6 or 4 minus 5 minus 6. And those don't give you the same answer. When there's a possibility of ambiguity like that, it's better to avoid it. It's better to avoid situations that could be misinterpreted. This is a meta feature of programming languages. Well-designed programming languages do not allow syntaxes that have an inherent ambiguity to them. I could pick either, I could say this means this, but you wouldn't know I meant it. How would you know I meant it to mean this and not this? And you could accidentally, somebody might look at that and say, well, that obviously means this. And somebody else might say, but that obviously means this. One of them is going to be wrong. Okay. Now, with addition, 4 plus 5 plus 6 is the same as 4 plus 5 plus 6. What's that rule called?
Associative
law, right. So because plus is associative, we can have multiple arguments. Subtraction's not associative, so it's bad to allow more than 2 arguments. Multiplication is associative, but division is not associative. So we'll allow 3 or more arguments for multiplication, but we'll stick to this is okay because of associativity. And this is not okay because of the lack of associativity. Did I spell that right? Let it change it. Okay. Okay. So for the multiplication operator, it's okay to have as many operands as we want. For the division operator, we stick to just 2 operands. That makes sense. There's no ambiguity. We're not going to allow division to have a bunch of operands. We could, but if we did this, we'd have to pick one of the associativities, and whichever one we pick, someone's going to say, you picked the wrong one. Whichever one you pick, somebody will say, no, you picked the wrong one. All right? Right. So our grammar allows addition to have an arbitrary number of arguments. Subtraction has, well, subtraction, if we go back over here, this is okay This is the unary negation operator. Okay. This, yeah. Similarly, okay. Now on the other hand, can you make any sense of that?
No, because it is a division and we need two operands.
Yeah, but there's some people who think that that makes sense.
Mm-hmm.
Can you, think of it. What could you possibly make that mean if you felt like doing it? There's one thing that kind of makes sense. Maybe what? Reciprocal. That's the only thing. Yeah, I mean, yeah, kind of. Yeah, I wouldn't do it. I would not make that mean reciprocal. But somebody might say, well, okay, divide by 5, you mean 1/5. Okay, I wouldn't do it. But you could maybe, you could, Now, that makes sense. Okay, that's the unary. Not, it's the positivity operator. It's like the negation operator. But it just doesn't do anything. The unary positivity operator takes 5 and returns 5. But it's actually a legitimate operator. Every language has it. You probably never paid attention, but this operator is actually in every programming language. It's the complement to that negation operator. Okay, so it's there. It's actually a legitimate operator in every programming language. It lets you write things like x plus y. If you check, that's legitimate. That's the addition of the positivity of y. So that parses as addition of the positivity of y. Just like if you did this, it'd be the addition of the negation of y. Okay. Another thing that's interesting, this, okay. What does that mean? Parse this for me. Read that off. What does that parse as? X space plus space minus space 5.
Could be x addition and -5.
Well, what do you mean -5? Be real careful. What do you mean? X added to what?
To the negation.
The negation of
The number 5.
5. Right. So that's two operators, the addition operator and the negation operator. Now, that does not parse the same way. How does that parse?
Okay.
That's not the same thing. What's different? What does this mean now? I'll give you a hint. This is a token. That's a unit, huh?
So it's a x plus -5. So like the first one, it was negation of the 5, but in this next one is just talking about the token as a whole, so it's a negative.
Yeah, so this
identifies
one's
as
got
negative
two
5.
operators. This one, if you looked at the assembly language code in C, for example, or in Java, you would see that this calls two operators, an addition operator and a negation operator. This calls only one operator, and this is the literal -5 stored in 2's complement. Remember, in 2's complement, you can store negative numbers. So this is the number -5 stored in 2's complement. This is the number +5. This negates it to -5 in 2's complement, but that's done, it's stored as a +5, then that operator is applied to the 5, then that operator is applied to the x and the 5. This applies the operator sum to x and the number -5, okay? So this here is the negation operator, okay? So that's, and this is the positivity operator. I don't even know what people usually call it. I mean, this one's always called the negation operator. This one, I don't know if people, I don't know, I actually don't know if there's a uniform name for this guy. I mean, you could call him the positive operation or the yeah, the operation that keeps a number positive, whatever it is. Oh, what's this? What's the value of plus -5? -5. Yeah, it doesn't do anything. The positivity operator really doesn't do anything, but it's part of the language. You know, it really just doesn't do anything. Yeah, because it leaves negative numbers negative and it leaves positive numbers positive. On the other hand, that is 5. That's the negation of -5. So that gives you the number 5. Okay. All right. So our language, you know, over here, we specify with this notation exactly how many operands each one of these operators is allowed to take. Now, our parser doesn't know about this stuff. Okay. Now, you know, what I was talking about over here is our parser does not know that division only has, the division has the rule that it's like, our parser does not know that a division tree is supposed to have 2 branches. Okay. Because our parser is a parser not of really this language, we're parsing the tree language. Okay, so that's what I was saying earlier. We could either write a better parser that parses this language, or we could write a parser that parses the tree language, but then we make our evaluator pay attention to this grammar. So it's our evaluator that's going to pay attention to this grammar for us. Okay, so that's important that we're pushing into the evaluator the actual checking of these grammar rules. We could have pulled it into the parser, but then we'd have to write a parser for every one of our languages. Language 1, language 2, language 3, language 4. Every language would need a new parser. And at some point, I'll actually do that as a homework assignment. I'm going to give you the home. At some point, I'm going to tell you to write the parser for one of these languages. Okay. Yeah, even though this is a subset of the tree language, so the tree parser will parse it. It'd be nice to write it would be worthwhile to write a parser that parses exactly that language and gives us parsing errors if we do things like that. We would get a parsing error if we did something like that. Okay, so here's what evaluate does. Evaluate takes in a tree. See, so eval a tree. The first thing it wants to know is what's the root of the tree. So it asks what the root of the tree is. Now here's a check. The root should be one of those operators, plus, minus, times, divide, percent, squared. If it's one of those operators, then it goes and evaluates the arithmetic expression. Okay, so if the root of the tree is one of these valid operators, then it calls a subfunction that evaluate the arithmetic. So that's evaluate arithmetic expression. Okay. Now, our language allows you to have just a integer number. So you don't have to have the tree can just be a single root that's an integer, okay? So if your root is not one of the operators, it checks if the degree is, okay, what this is doing is, suppose I put an @ sign, suppose I called suppose my tree looked like the following. I don't have an @ operator, but that'll build me a tree. That will build a tree with an @ sign at the root and a left branch and a right branch of 4 and 5. So that will parse to a tree, okay? So my evaluator should somehow figure out that that's not legitimate, okay? So the evaluator says, okay, you're not one of these operator nodes, okay? That tree does not have degree 0. See, that tree does, this illegitimate tree has degree 2. So it skips over this guy, and it then gets to else. Well, you gave me, then it says invalid expression. It was not one of these operators, and it was not degree 0. See, if it's not one of these, the only other option is integer. If it's not one of these, the only other is integer, and integer is degree 0. There's no children under the integer, okay? So the evaluator says, if you're not one of these, and you're not degree 0, something's wrong. So that would throw an evaluate error. This guy wouldn't evaluate. Okay. Now, another problem is, what if the tree just looks like that? X. That's a tree with a single root. Okay. That would be not one of these, but it does have degree 0. But then that node would not match this regular expression for integers. So this would not be true. So then you'd get invalid expression. So that would catch the X by itself. Okay. So there's the first level of parsing. The evaluators both evaluating and parsing. Actually, this step is really a parsing step. It's checking that you have a proper root node. Okay. If you have a proper root node, it goes and evaluates that root node. Then it checks that if you have a single node by itself, that it matches the integer expression. Otherwise, you get that evaluate error or you get that evaluate error. Okay. So now that leaves, and if this thing matches an integer expression, the return value is just the integer value. So then the evaluator returns the result of parsing the integer. If it's one of these, you call this guy, and then whatever he returns, that's the result, okay? So you either evaluate the tree node with this, or you evaluate the integer with this, and you return the result. So that leaves this guy to figure out. See, that's the other function in here, okay? So now he's supposed to evaluate one of the arithmetic operators, okay? All right, so he gets the tree node, he gets the node. The node is the operator, okay? So he's got this string is either a plus, a minus, a multiplication symbol, okay? Every one of these operators has a left branch. Every operator is, if you go back up to the grammar, every one of these operators has at least one operand. So there's always a first branch, okay? So down here, after you get the root node, you evaluate the left branch. See, that's subtree 0. There's guaranteed to be a subtree 0, okay? But there's not guaranteed to be another branch, because unary negation only has one branch. Unary addition has only one branch. This could have one or more branches. This is supposed to have exactly 2 branches. This is supposed to have exactly 2 branches. This is supposed to have exactly 2 branches. It actually, only these first 2 could have one branch, but the others, but those 2 could have just one branch. So now we've got the left branch, and we have a declared variable to hold the result for the right branch. And now we check, does the tree have degree more than 2? Okay. If there is a second branch, evaluate it. Okay, so if there's a second branch, evaluate it. So now we've evaluated a first branch and a second branch. If the tree, now we start specializing on exactly what tree it is. It could be a plus tree, a minus tree, a multiplication tree, a division tree, a remainder tree, or an exponentiation tree. Notice that if it's one of these, it just uses the left and right branches. These are the trees that are required to have exactly 2 branches. So there's the left branch, right branch, left branch, right branch, left branch, right. Notice that this one uses the Java division operator. This one just uses the Java division operator on the 2 results to do the calculation. And exponentiation calls the math.power function in the Java library. So my interpreter falls back on my host language to actually do the real work. When it comes time to exponentiate, how am I actually doing the exponentiation? Well, I let Java do it for me. Now, this is where I'm kind of cheating. My interpreter is making use of the fact that it's written in a programming language, and that programming language knows how to do these operators. Okay, if I was writing a compiler, this would be a little bit trickier. See, to write a compiler, I would have to like spit out code that either called somebody's exponentiation function or called some machine instruction that did exponentiation. You know, a compiler could do either one, but I would have to spit out code that would do that. Here, I just call Java's library function for do exponentiation. Okay, now those were the operators that took exactly 2 operands. The tricky ones were multiplication, subtraction, and addition. Okay, addition could have 1 or more operands. So here it says if it's an addition with degree 1, then the left result's done. We're done. That's the result. Else, we add left to right, and then we iterate through any other branches there might be. Addition could have more branches, so we iterate through the further branches of the tree. So you have to kind of think of a picture, imagine somebody did plus of 4, 5, 6, 7. Okay, that's a tree that looks like this, plus of it's a tree with a bunch of branches. The code is going to, the way the logic of the code works is it gets the first operand, gets the second operand. If we go back over here, grab the first operand and evaluate it. If there's a second tree, evaluate the second branch, branch 1. If it's a plus, okay, we have degree more than 1, so we're in this else clause. Well, what do? We add left and right together. So you would add 4 and 5. Then you'd start iterating on 6, 7, and 8. So then you start iterating on these other branches. After you've grabbed the first branch and the second branch, now you just iterate on however many branches there are. So you go into a for loop that iterates from 2. You're going to start iterating here on a third branch. Iterate from 2 up to the degree, and you integrate. You take each branch, evaluate it, and add it into the result. So you first grab that branch, then you grab that result, then you drop into the for loop that iterates across these and adds 6 to 11, then adds 7 to 17. So then it adds this number to the sum of these, then it adds this number into the sum of those. Okay, so that's the logic. And it's a little bit tricky, but if you draw pictures of trees, you should be able to. The truth is, when you write code like this, you should always have pictures in your mind of trees. you don't really just write this code. I mean, you imagine these trees and you think, what would I do with that tree? Okay, because you also have to, you have all these other cases. You have plus 4, that's a case. Plus 4, 5, that's another case you have to handle. Plus 4, 5, 6, that's another case you have to handle. This case is handled by one branch of the code. This is handled by another branch. This is handled by that for loop, but it'll only iterate one time. This is handled by that for loop that's going to the for loop's going to iterate 3 times. But I have to be ready to handle anything from 1 branch to 2 branches to 3 branches or more. Okay. Again, the first branch is grabbed here because every operator has a first branch. Then I say, if there's a second branch, go ahead and grab it, because many of the operators have a second branch. Then I say, if I'm a plus, then I check. Do I have only 1 branch? If I did, I'm done. Otherwise, I've already grabbed the first 2 branches. Now iterate through the further branches. Okay. Minus is a little bit different. Minus only has the cases of the minus one only has minus 5 or, whoops, it only has to handle 2 cases, 1 operator or 1 operand or 2 operands. So the minus only has to handle 2 cases. Okay, so if the degree is 1, we return the negation of the left branch, of the first branch. Else, we return the subtraction of the 2 branches. We've already grabbed them, so now that we know that it's a minus, we either negate the single branch or we return the subtraction of the 2 branches. Multiplication looks a lot like addition, but remember, multiplication, multiplication only handles this or this or more, so it doesn't have the single. Multiplication doesn't have the single branch case to it. So for the multiplication, you start off by multiplication is supposed to have at least 2 branches. So there's the product of the first 2 branches. I call them left and right, but that's probably pretty bad names. It should have been first and second. I just called them L and R. I really think that I probably should change those. Maybe this should be our result 0 and result 1, but 1 looks like an L. Yeah, it's really branch 0, branch 1. I kind of, I call them L and R, thinking that in the case of a binary, this is the left branch and this is the right branch. When there's two operands, it's sort of like left and right. But when there's more than 2 operands, it's really 0th operand, first operand, second operand. 0th branch, first branch, second branch, third branch. Okay, so naming things is hard. And in my code, I have to make choices in names. I argue with myself a lot over these choices. Like, is that a good choice? Should I call them left and right, or should I give them names like result first, result second, or result 0, result 1? Okay, but the negation operator only has to worry about 2 cases: 1 operand, which case it negates it, or 2 operands, in which case it does subtraction. And notice that in Java, that's negation, that's subtraction. Now notice Java uses the same operator. Your TI calculator doesn't. Your TI calculator famously has 2 different keys for negation and subtraction. But the Java, C, C++ languages, they use the same symbol to mean the unary negation and the binary subtraction. Okay. Multiplication, let's see, multiplication. So subtraction has 2 operands. Multiplication has to deal with 2 or more operands. So there's the 2 or more operands. And then these guys did just 2 operands. Okay, so there's the evaluator. Okay. The first step is actually the error checking. Okay. Oh, notice that I do not completely correctly error check everything. Does anybody see a missing error check in this code? my evaluator ignores a possible error and lets it slide by.
More than one division symbol.
Yeah,
Um,
if somebody gives my evaluator /345, it will return the division of 3 and 4 and skip the 5. It'll just never get to the 5. It'll just do the division of 3 and 4 and not even pay attention to that. My evaluator isn't doing as much error checking as it should be doing. So right here, what could I do? How could I fix that?
Could you throw an exception if more than 2 operands get returned?
And where would I do that?
Somewhere inside the else if note
Yes,
equals.
yeah. In
division.
here, I would have to do one of these throw exceptions. I would have to say, if the degree is greater than 2, throw an exception. If the degree is greater than 2, throw an exception. So it would look like this. I would do, I'll just copy and paste. Okay. It'll be if tree dot degree is greater than 2. Now it shouldn't be, for a division, it shouldn't be. If tree dot degree is greater than 2, I could just say invalid expression, or I could maybe give a more specific one. Okay. And then that would also go here. And that should also be here. And this one would say explanation should have 2 operands, and integer and remainder should have 2. Okay, that would make my evaluator a little bit more careful. What does all this error checking do? It slows down the evaluator. Have you ever heard that Python is a ridiculously slow language?
Yes,
Do you know why it is?
because it has to interpret every time you run it. You don't have an executable file. Well,
And
you can make an executable file.
Yeah, you can, but more than that, do you see where the slowness is coming from?
You don't have that portion of exception handling like
No,
going
what
on.
is my evaluator constantly doing? It has to keep checking things. It has to do constant error checking as it's evaluating my program. Think about it. When does a compiled language like C check for errors?
When it compiles.
Yeah. Then when it runs, it knows the errors aren't there. When does an interpreted language like Python check for errors?
While it's while the program is in process.
Right. So suppose you have something like this. Okay, here's an example. Suppose you write for int I equal 0, I less than 1 billion. Okay, and supposing that I do division of x, y, and z. Or actually, just make it correct. Division of x and y. Okay. Now think, this is my interpreter. Suppose this is Python-like, my interpreter-like. This for loop 1 billion times has to do what? It has to 1 billion times check, is that tree branch degree greater than 2? See, because the interpreter will loop through this a billion times. When it hits that guy, every single time it hits that guy, the interpreter says, oh, is the tree degree greater than 2? Because if it is, I should throw an exception. But what's stupid about this?
You really only need to check that once.
Right, but the interpreter doesn't know that. And trying to make an interpreter that knows that's really hard. A compiler only checks it one time. A compiler checks that there's 2 operands to that operator, says fine, and it compiles the code and it runs fine. The interpreter, every time it loops and it hits that line of code, the interpreter has to recheck, are there 2 branches? And this is one of the reasons why Python's crazy slow, because the interpreter is doing all this runtime checking over and over and over again. And it literally, in a loop like this, would do the same error check a billion times. Now, there are ways to try to optimize that stuff out. And some Python, like I said, you can compile Python to intermediate code. And when it compiles intermediate code, I think it does fix this problem. But if you run it in the traditional Python interpreter, the interpreter just does this, what we're doing here. The interpreter just keeps looping on the same conditions over and over again. Okay, so this is what makes interpreters real slow. It's one of the things that makes interpreters slow is the constant need to error check over and over and over again. A compiled language only would check that thing for errors. A compiled language, if it saw a Z there, would just stop the compile and give you an error message. You know, slash only has 2 operators, so your program won't compile. Okay, but an interpreter like Python, even when it's okay, a Python interpreter probably would stop the first time it looped and say, that's only supposed to have 2 operands. So you'd get an error message on the first iteration of that loop. Fine. The trouble is when there's no error, but the interpreter keeps checking over and over and over again. Every time it hits that division operator, it keeps checking again, does it have more than 2 branches? That's what that's what drives interpreters bad, is the need to constantly check for errors over and over again. Okay, let's see. Okay, all right. So now my interpreter, actually, that actually should be in my. I'm going to leave it there. As every time I go through these, I notice little things that I forgot to do. Okay, this interpreter should have this in there because it should catch the error that there are too many operators to the operands to division, or there's too many operands to division. Okay, so that's a good thing to have in there. It slows it down, but now it catches an error that would otherwise slide by. Okay, now let's play around with, okay, I've got a couple minutes left. See this batch file that says language 1? What I did is I wrote a build script that compiles all these code into a jar file. And then this runs the jar file. What that gives you is an interpreter of this language. Here, watch what. Here's a language 1 interpreter. What's the product of 3, 4, and 5? Okay. What's the sum of 4, 5, and 6? What's the division of 6, 3, 2? Notice that this is the version that didn't give me an error message. Now, let's rebuild the language. Okay, to rebuild the language, I clean up everything. Okay, call this build script that builds all the classes. Okay, that built all the classes. Then call this build script that builds the jar file. Okay, there I rebuilt the jar file. So now this jar file has that little bit of extra code. Now I can call clean and get rid of all the class files because all the class files have now been built into this jar file. Now I can run this guy and let's see what happens if I do the division of 6, 3, and 2. Okay. See, now I added a feature to my language is better now. Now it caught the eval exception. Slash should have 2 operands. Okay. And if I do now watch, if I do the sum of 4, 5, the product of 5 and 6 with the division of 2, 3, 4. Okay, notice that there's a problem in here. There's no problem. Okay, now so you notice how it found where the error is. I have an eval exception in this part here. Okay, so my interpreter caught where the error was, and it gives you a little. It tells you where. Now, if this was a much bigger expression, it should report exactly what line number and character position the error was at, but it just tells you that that was the expression that was wrong. Okay, and it should catch division operator. See, what if I do 1 operand? Whoa! See, now I've got a mistake. See, my interpreter still got some problems in it. Notice that crashed the interpreter. Okay. I was looking at this the other day. I forget what's doing this. See, that crashes the interpreter. If I run the interpreter again, I can get a little bit of a hint what's going on wrong here. Okay, but notice it built the expression tree. And here I get a hint of what's wrong. No, that's the right expression tree. It's a percent with 1 branch. Okay, it's a percent with 1 branch. Let's actually see if we can figure out. Okay, let's go back and see if we can figure out where the evaluator is doing this wrong. Okay, let's see. Okay, the evaluator comes in and says, it's that node there. It's a percent, it's an integer division, it's a remainder operator. So it calls this method. Okay, so we're in here, okay, and we tree element, okay, get the element, that's this guy. Evaluate the left branch, that's this guy. If there's a right branch, evaluate it. Well, there's no right branch, so I don't evaluate it. Okay. I'm not a plus. I'm not a minus. I'm not a star. I'm not that. I'm this. Okay. Now, oh, I see real quick. Now, what's my mistake?
The expression result equals result left modulus result right. You don't have the option for if it's just one.
So what, how do I fix this?
Make another throw exception.
I wouldn't do, no, think better.
Oh.
I can do better than that.
You could just leave the result equal to, or if there's just 1 operand, then oh, you could put an or in there, yeah.
Yeah,
If
if
it's
tree dot degree
less than
equal 1 or
yep.
tree dot degree greater than 2. See, I shouldn't, see what's happened. This is a null pointer, except, this thing doesn't exist for this guy. See, it never evaluated our result R. So if the tree degree is 1 or greater than 2, so I should take this and put it in there also, and put it in there also. Okay, so rebuild the language. So build all classes. Build the jar file. Test the language. Okay, see, fixed it. If code is well designed, it's not that hard to fix things. Yeah, yeah. But how do you, but you need tests. I mean, see, one thing I haven't had time to do is write a lot of unit tests. See, by playing around, I saw that, I saw that I created I essentially created a test and failed it. When I failed the test, it didn't take me very much time to fix it. But until I have a test I can fail, I don't know I have an error. Okay, so you need a well-designed system should have a whole suite of unit tests. And right now I have this one file here. No, not that one. That's not a very big suite of tests. And it's not testing for error conditions. So I should have a bunch of tests that test for things that are possible errors. I should have lots and lots and lots of error tests. And I just haven't had time to write them. Okay, so we stumbled on a couple right now and we fixed them. Okay, so so now we've already put new tests into the evaluator to catch possible grammar errors. Okay, all right. And if you play around with the language enough, you'll probably get other things that crash the language too. I think, let me see. I think the other day it's I can't wait. Does anybody, I remember there was something else that crashed the language the other day. We saw something the other day that crashed it, and I can't remember what it is now. I remember we did something that crashed the interpreter. Okay, now that's language one. Okay, the heart. Now, if you go through this folder, language one consists of this thing that builds the trees. Okay, now this thing uses, and if it sees an error, that throws that parse exception. Pretty printer prints out the trees in a nice way. Okay, this is a test program, test program, test program. This is the read eval print loop. This is the code we just did, and this is the eval exceptions. The only thing we haven't talked about is this this one up here. If I run this program here, here's an arithmetic expression written in prefix form. But we're not used to prefix notation or tree notation. Here's the notation we're used to. So that program abstracts syntax tree to infix. It takes these tree expressions and writes them in that nice parenthesized infix notation. Okay, that's what its job is. It's supposed to take an abstract syntax tree and do a pre-order traversal, which is this guy. See, this is the pre-order traversal. Well, I'm sorry. This is the, no, I'm sorry. It's supposed to do an in-order traversal, but with parentheses. It's supposed to do an in-order traversal, but add the parentheses that group things appropriately. Normally, an in-order traversal just prints out the symbols in order, but this one here, it does an in-order traversal with parentheses, grouping things properly. Okay, and it does it two ways. One way groups it entirely, and one way groups it minimally. See, if you think about this expression, it only needs that pair of parentheses there. So the other parentheses were redundant. So this one is a fully parenthesized version of the expression, and this is minimally parenthesized. Okay, so that's what that code does. And you can look at it. In your next homework assignment, you'll have to modify that piece of code to do some more work. Okay, so that thing it's a form of like a pretty printer, but what it pretty prints it in parenthesized infix notation. The actual interpreter is only the parser and the evaluator. The parser with its parse exception, the evaluator and its evaluate exception. That's the actual programming language. This is a pretty printer. This is a pretty printer. They just rewrite the tree in a nicer way for you. They're just things that rewrite the tree. Okay, so they're not part of the language. They're essentially like tools that just make the language a little bit easier to read. Okay, instead of reading that, you might think, well, okay, that's a little bit easier to read. At least it shows you the tree structure. And this shows you what it really means. This shows you, oh, it's 4 times 5 plus 100 divided by 5 minus 15. So this in its standard infix notation. So that's a tool that takes the prefix, the tree notation, and turns it into what we're used to reading. Okay. So the language is just the parser and the evaluator. That's the language. Parse into a tree, walk the tree. Take an expression, parse it into an abstract syntax tree, walk the abstract syntax tree. That's going to be our language. Yeah, that's what our interpreters are. Two-step process. Parse, walk. Okay. All right. So that's the, and then, this is the, and this file describes the tree data structure. So the parser gives back tree data structures. This traverse is just simple in-order, pre-order, in-order and pre-order and post-order traversals of the tree, which are not, I should delete, actually I should delete that. That was only interesting in language 0. It really plays no role. I think I should delete that from this folder, because traverse was interesting with trees, but traverse is not really interesting for these languages. It doesn't really make any sense to traverse this language. Okay, that's really what this guy's there for. This guy replaces this one. Okay, this one traverses the tree in an in-order traversal and prints it out nicely like this. Okay, all right, then on Wednesday, we'll look at language 2, which just adds Boolean expressions to the evaluator. So the evaluator is going to have a couple more clauses in it to handle Boolean expressions. The language will include Boolean expressions, but the key, the thing that'll be interesting is now there's 2 data types. There's integer data types and Boolean data types. So what we'll talk about on Wednesday is how we add a new data type to this language. That's going to be the real crux of the matter, is adding a new data type. Okay, so so we run out of time. If you have questions about homework assignment 1, send me emails or come to Zoom meetings. And like homework 2 will probably be up there later this week, because actually we have to get to language 3 before you can do homework assignment 2 anyway. So maybe it won't even be up there till next week, because it'll take us at least, probably on Wednesday we can finish language 2 and start language 3. And then you could start, then you at least you'd know enough to start looking at homework assignment 2. But until we talk about languages 2 and 3, homework assignment 2 isn't going to make any sense. Okay. All right. Anybody have a last second question? Any last second questions at all? Okay. So I'll go ahead and stop sharing, and I'll end this, and we'll meet again on Wednesday. Okay. Bye.